Hello everyone, so today we are going over concept 3-13, viscous and drag forces. So let's get started with this first question here, and I have the applicable equations for today's lecture written right here, but if you do have it, pull out a calculator as well as your formula sheet so that you can follow along with me with the concepts we're covering today. And if you don't have a formula sheet, there should be one linked in the description below. If not, yell at me about it in the comments. So, okay, let's get started. A small fish is subject to both viscous force and drag force from the water. If the fish swims twice as fast, what happens to these forces? So, right away, I have listed out both the viscous force equation as well as the drag force equation. And for this problem, we are only going to be focusing on the value of velocity in both equations. And what we're going to do for both cases is imagine all these other values are held constant. So if we imagine they're both all held constant, where velocity is the only changing factor, we can say that the viscous force is proportional to velocity and the drag force is proportional to velocity squared. Because we said, like, let's just imagine all these other values are 1. All these other values are 1, and then this coefficient doesn't change. This coefficient of 6 and 1/2 don't change, so they don't impact the relationship between drag force or viscous force and velocity. So let's imagine we just plugged in velocity of 1 meter per second for both of these values, 1 meter per second and 1 squared. We would see that f of v would be proportional to 1 in both cases, and f of d would be proportional to 1 squared, which is equal to 1. But if we doubled it, if the fish was going twice as fast, if its velocity doubled from 1 to 2, we would see that the viscous force is proportional to 2v, and when we plug everything in, we see that it is equal to 2. But if we do that same thing for the drag force, we see that we just plug it in, and we see that when the velocity is doubled, the drag force increases by a factor of 4, right? So as for these to be equal with one another, the drag force must be 4 times its initial amount listed up here. But in contrast, the viscous force must only be twice its original value. So if you are to double your speed, then the viscous force doubles, but the drag force quadruples. And just imagine that these are a direct proportional relationship. So as f sub v increases, so does velocity. As one decreases, the other one decreases as well. Let's move back up. For f sub d, as v increases by a factor of 2, so let's say times 2, the force of drag must increase by a factor of 4 to compensate because it's v squared. That squared value in front of it are in the squared value here as the exponent means that whatever you are increasing by, you have to square it in order to determine the force of drag. Okay? So if we're looking through our answer choices, choice A says the viscous force and the drag force are double. That's false. We just said that the drag force would be quadrupled if velocity doubles. The viscous force is doubled and the drag force is quadrupled. That one is true, so that's correct. Both the viscous force and the drag force are quadrupled. That is not true because the viscous force is directly proportional to the velocity. And if velocity increases by a factor of 2, then viscous force should increase by a factor of 2. But the drag force is proportional to the velocity squared. So as velocity increases by a factor of 2, when the exponent is applied to 2v, we see that the drag force must be increased by a factor of 4 to be the same as the velocity, to experience the same increase as velocity increased. So therefore, C is false. The viscous force is halved and the drag force is doubled. This one just doesn't make sense because we doubled the speed, and this would suggest that the viscous force has a inverse relationship. So as the viscous force increases, 1 over velocity increases. So if we doubled this, it'd be 1/2. But that is not the case for the equation. So that is false. Oh, and let's just imagine all that text isn't there. And then finally, E says the viscous force is halved and the drag force is quartered. This would, applying this further, this would suggest that F sub D is equal to 1 over V squared, which is not the relationship that we see in the equations listed here. So B is our answer. Moving along here, we have 3-13-2, and it says, if the Reynolds number is much greater than 1, how does the drag force compare to the viscous force? So the equation I have listed out here is the Reynolds number is equal to, this is the drag force on top, and this is the viscous force on bottom, times R sub V. So if we are looking at this equation here, we see that we can look at the relationship between RE and P over mu, or that's some Greek letter, I don't know. But anyways, drag force over viscous force. So if we are to say that the Reynolds number is greater than 1, then what must this fraction, what is the relationship of this fraction here? If we were to say that, let's say Reynolds number was 2, what would this fraction have to be for the Reynolds number to be 2? It would have to be 2 over 1, or 4 over 2, 6 over 3. And we said that the drag force is the numerator and the viscous force is the denominator. So if the Reynolds number, is greater than 1, if it is greater than 1, that must mean that the numerator is greater than the denominator, which then means that the drag force is greater than the viscous force. And if we look at our answer choices here, we see that A is the answer. If we look at the rest of these option choices, D, we have enough information to tell because it's a pretty straightforward relationship. There aren't any extraneous factors that would play a role in calculating the Reynolds number. C, the drag and viscous forces are equal. This would only occur if the Reynolds number is equal to 1. And then the drag force is smaller than the viscous force. This only occurs if the Reynolds number is less than 1. The next question we have here is asking us to examine the relationships between force and velocity for 3 different types of resistive forces. So we have 3 separate lines here. One that looks somewhat quadratic. It looks like it's going to go in this, something like this motion, or this movement. We have a horizontal line suggesting that as velocity increases, there's no change in force. And then we have line 2 here, which looks like a linear relationship. So we have a quadratic relationship, a linear relationship, and a no relationship. So those are the 3 relationships that we see on the graph here. And what we're asked to do is compare these relationships of force and velocity to the equations that we know that are given on our formula sheet, but we can also analyze directly. So let's start with the easiest one, the horizontal line. So as we just said, this suggests that there is no relationship, relay. I'm just going to leave it like that, relay. And I'm going to go back to the color blue. So that means that we have to look at the equation that has no relationship between velocity and the force being applied. So if we look at these 3 equations, we see that the force of kinetic friction is equal to the kinetic frictional coefficient times the normal force. So as we can see, there is no influence of velocity within this equation because velocity is not included in this equation, which must mean that the force of kinetic friction is independent of velocity. So therefore, 3 3, the easiest one, must be F sub K and also F sub S, because that's another frictional relationship. So we are saying that the force of friction is independent of the velocity that the object is moving. Let's look at the next two, 2 and 3. So already, before we do so, we already see that since 3 is this horizontal line, and we know that 3 is friction, we can cross off answer choices A and B because they do not place friction as option choice as line C. So we see here, these are not correct, and that is why they are false. So, okay, let's look next at option number 2, this linear relationship. So as we just stated, the viscous force has a direct linear relationship with velocity. So as velocity increases by 2 times 2, the force of the viscous force increases by a factor of 2 as well. So we'd see a linear relationship develop because as one increases by whatever factor, we could say factor of 10, 20, the other would increase by that same factor. So that's why we see a linear relationship when all other variables are held constant. So as such, the viscous force would be line number 2. And let's just analyze line number 1 because we should. It's good practice to analyze all our information. When we look at this, we see that there seems to be a quadratic relationship because as velocity increases, it seems that the frictional force is increasing by a factor greater than 1. So therefore, when we look at the drag force, I don't know why I put G there. It should be D. When we look at the drag force that we've written out here, we see that F sub D is proportional to V squared. So as V squared increases by a factor of 2, the drag force must increase by a factor of 4 so that they can continue being directly proportional to one another. And as such, we see a quadratic relationship form between these two variables. And as such, D is our correct answer. Okay, so our final question here is 3-13C, which asks, a skier is moving with a speed, so we're already thinking velocity, of 5 meters per second, encounters a drag force from the air through which the skier passes. The skier's cross-sectional area is 0.6 meters squared. The drag coefficient is 1.0, and the mass density of air is 1.2 kilograms per meter cubed. What is the drag force? So already written out in front of us, I have the equation for drag force. So drag force is equal to 1/2 times the drag coefficient times the mass density of air times the cross-sectional area of the object and times the velocity squared. So this is pretty important. We see that velocity is squared. So with a velocity of 5 meters per second, it would eventually turn into a value of 25. So this question is honestly just a plug and chug to get the answer. We just have to plug in the correct values to the correct things. So 0.6 meters cubed, or meters squared, is this value here. 1.0 is the C sub D. The mass density of air is this P value. And velocity is V. So when we plug all those in, we get 1/2 times 1.0 times 1.2 times 0.6 times 5 squared. So simplifying this out, 1 is just 1, so it's not relevant to the equation. 1/2 times 1.2 is 0.6. 0.6 times 0.6 is 0.36. And then 5 squared is 25. So we can then just write F sub D is equal to 0.36 times 25. And when we multiply this out, we get 9 newtons. So the force is in newtons. The force of drag is 9 newtons for this particular skier. And that is the answer. That's how we go through it. You could also if you were given 9 newtons and you weren't given the velocity, you could solve for velocity if you had all the other variables. Just keep this in mind, how you'd rearrange these equations to solve for different variables, and just kind of test it out. Use the same information, but get rid of a different variable. Get rid of the cross-sectional area, for example, and see how you'd solve for cross-sectional area. And this is a good way of better understanding the relationship between these variables. You can also just say, I'm going to hold everything constant except velocity, right? Let's say I held the cross-sectional area, the mass density, and the coefficient of drag constant, but I doubled the force of drag. How would that impact velocity? How would the velocity change for this equation to still be held true? And that's a good way of testing your knowledge of the relationships between these variables. So that's our last question. I hope you enjoyed. If you did, please give this video a like, subscribe, do all that other stuff. It's greatly appreciated.